quiz. And the quiz is going to be only on chapter 18. Okay. It's going to be a 30-minute quiz. I'm going to send an email to remind you. Okay, it's going to be a 30-minute quiz. All right. So after the quiz, we're going to solve some problems. I want to revisit the animal with you guys because I'm thinking of. I look at the performance on the online homework. It doesn't seem. Well, a lot of people got 100, right? So I'm not looking at. I want everybody to get 100. Let's put it that way. Okay. So I saw some performances there that I didn't really like. So I'm thinking of opening up another section of the NMR homework, and it's going to be bonus. Okay. So I'll revisit that on Wednesday after the quiz, so as to help you guys understand it better. It's very simple. It's just trying to recognize what protons are you dealing with where. Okay. Usually it's the proton NMR that gives you trouble. Okay, so just to let you know. So the quiz on Wednesday is going to be 30 minutes. Okay, not 50 minutes, but 30 minutes. Okay, and it's going to be group quiz. So you'll be pairing up with a partner. It's only going to be SP, hybridized. We're not going SP2. Okay, so it's only SP, you and the partner. Okay, all right, so okay. So let's continue from where we stopped. We've dealt with naming of aldehydes and ketones. Now we're going to talk about how to make them and the reaction they participate in. Most of the reactions that you're going to be seeing here are reactions that you've seen before. So I actually looked at the online homework and some people have finished this section. I'm like, we've not even covered it and finished. I mean, what do you want me to do, right? So it's like a waste, I don't know. Like, so that's awesome because most of the reaction here are reactions that we've talked about. Again, you should remember that organic chemistry reactions is just transforming one functional group to the other. Okay, so if we've talked about the alcohols, we've definitely talked to a certain extent about aldehydes and ketones because you can oxidize alcohols to ketones or aldehydes. Okay, if we're talking about the reaction of how to synthesize aldehydes, we've dealt with alkenes. Oxidative cleavage of alkenes, ozonolysis is an example of that, right? So we're converting alkene to aldehyde. In alkynes, we've done the same thing, right? Converting some alkyne functional group to aldehydes, terminal alkynes. So those are the reactions that you're going to be seeing here. We're going to breeze through it. But I'll encourage you to revisit those functional groups, alkenes, alkynes, alcohols, right? Okay. So the first reaction that we're going to consider is converting alcohols to aldehyde. So if you have primary alcohol, you can convert that primary alcohol to aldehyde using PCC, which is a mild oxidizing agent. Just call it mild oxidizer or oxidizing agent. Or you could use Des-Martin's periodinane. Okay? Des-Martin's periodinane. You know that reagent? Oh boy. Should I draw it out? Let's just leave it. Okay? Let's just leave it. Alright. Not to scare you guys. So just Des-Martin periodinane oxidation, you can use that to oxidize primary alcohols to aldehyde. So this is the aldehyde functional group. So when you're studying, try to highlight that. And this is the alcohol functional group that you're converting. Okay, so the carbon chain is going to remain the same. The functional group site is what the difference is. Okay. So the second reaction is oxidative cleavage of alkenes through ozonolysis. So in the presence of ozone followed by zinc in acidic medium, you can oxidize. Let's change this to hydrogen so that we know we're dealing with aldehydes. Okay, so you can oxidize any alkene that has vinylic hydrogen. So any hydrogen sitting on double bond are referred to as vinylic hydrogen. Okay. So those are the vinylic hydrogen. So if you treat that alkene with ozone, you can cleave that double bond. Okay. Remember how we did that? So you cleave the double bond. Just going to redraw this out here so that you see how that formed. Just a reminder. We just add oxygen to one end of the double bond and oxygen to the other end of the double bond. So that's how you get your oxidative cleavage, right? So this is the same thing as this. Okay. Here's another example. You have vinylic hydrogen here. You have two vinylic hydrogens there. So when you oxidatively cleave these bonds, you're going to get, in this case, two aldehydes. Okay. Plus those two hydrogens that you have on the other side. Okay. So that's for oxidative cleavage of vinylic of alkenes with vinylic hydrogens. Now we've talked about reducing esters to alcohols using a very strong oxidizing reagent in lithium aluminum hydride. The ester group is unreactive to sodium borohydride, but there is another mild reducing agent that can partially reduce your ester functional group, and that reducing agent is called dibal. Sometimes they say dibar. In some you see dibal. In some you see dibal H. Okay, so they call it different names. All right. This is the structure of the dibal. It's a diisobutyl aluminum hydride. So you can see the hydride there. And the reason you can partially reduce these esters, let me just use a generic structure here, showing the ester functional group. The reason you can partially reduce this is because your dibar is supplying the hydride ion that you need, and this ester group that you have, the alkoxide there, is a very good leaving group. Okay, so they are very good leaving groups. Okay, so what happens is, mechanistically, if you treat this with your hydride from the dibar, so I'm just going to write H- from the dibar, that's going to act as a nucleophile attacking the carbonyl carbon. You have this alkoxide form, the OCH3 with the hydrogen from the hydride. Okay, and because this is a living group, your carbonyl is going to reform, and your alkoxide is a better living group than your hydride. So instead of kicking out this hydrogen again, this methoxide is what is going to leave in this case. Okay. So now you have that aldehyde plus, okay, which is going to bond with your aluminum. Okay, it's going to coordinate with your aluminum that you have in the dibar. So it's going to be trapped in there. You can isolate your aldehyde functional groups. Okay. So that's how that works. Okay. So that's for aldehydes. So how do you make ketones? Well, the reaction is similar in making ketones, but the substrate is different. So you can do oxidation. You can do oxidation of secondary alcohol. Secondary, so this is a secondary alcohol here. You can use your PCC, or you can use Jones reagent, which is you can use your chromium-based reagent. Right. Okay. I think let's see. Okay, so we can use our chromium-based reagents, Jones reagent. This is okay in acidic medium. What else can we use? I'm sorry?
Can you use DMP?
Well, you can use desmatic pyridine too, but that's just going to take longer and it's more expensive, right? But usually for secondary alcohol, since there is no further, let me take that back. But generally, we assume that when you oxidize secondary alcohol to ketone, there is no further oxidation. But I've shown you an example where you can actually have some of the ketone further oxidized, because that ketone can tautomerize to enol that can then be oxidized like a double bond. So, but generally, when you oxidize secondary alcohol, you get a ketone. So we'll assume no further oxidation can occur. So if you want to use desmatic pyridine, it's reactive towards it, so it will get there. Okay.
Is it slower?
It's slower and more expensive, so people will not use that. You just throw your chromium base there, you get what you need. Okay. So, but any of these reagents can work with desmatic pyridine. But if you're using primary alcohol, you cannot use chromium base because that will further oxidize it. It's a stronger oxidizing agent, so it's going to push it further to carboxylic acid, and you don't want that. So that's why you're using PCC and DMP for aldehydes. But every oxidizing agent you can think about can oxidize your secondary to ketone. Okay?
So don't use the chromium for secondary rather than primary alcohols.
It depends on your synthetic goal.
Okay.
So if your goal is to make carboxylic acid, then you have to use chromium base. Okay? But if your goal is to make aldehyde, because we are talking about aldehyde, then you stick with PCC and DMP. Make sense? Good. Okay. All right. Well, let's worry about the mechanism. You can review the mechanism. We've talked about that. I have some paper here I can use. Let's keep that aside. Okay. Also, you can do ozonolysis of alkanes, so oxidative cleavage of alkanes. So, in oxidative cleavage of alkane, you can cleave an alkane that is disubstituted, trisubstituted, or tetrasubstituted to ketone. But you have to be very, very careful in identifying which of the section of the alkene is going to be converted to your aldehyde, which is going to be converted to your ketone. So you're slicing this into two. The bottom part, so when you slice this into two, I like to draw this out so that you first see the way the slicing takes place. So when you slice this into two, you get this. Okay? So you're just inserting oxygen in between the two double bonds, right? Oxygen there, oxygen there from the ozone. Okay? But this is a bad example because it's giving you aldehyde and we're focusing on ketone, so this is the ketone you need. So how can you make this a ketone completely? Well, you can tetra substitute the alkene. So if you look at this alkene that we have here, it is tetra substituted. That means it has alkyl groups on all the carbons. There is no hydrogen at all. There is no vinylic hydrogen on the double bond. So when you click that oxidatively, you're going to get two ketones. So you click it, it's come here. Okay, and that's what you get. And your reagent is ozone under acidic condition. So even though here you're given a metal as zinc, it's not limited to zinc. So you can use iron, you can use tin, you know. So just to let you know. All right. Okay. Another reaction we've talked about that was in chapter 16, benzene and aromaticity, is Friedel-Crafts acylation reaction. So if your goal is to synthesize aryl ketones, okay, what are aryl ketones? Remember we talked about the aryl groups. So this is your aryl group. Okay. So when you want to make aryl ketone, you can do Friedel-Crafts acylation reaction on aromatic ring. So you use your acid chloride. For this specific example, you're using acetyl chloride, but the generic formula for that would be, okay, where X could be halogen, right? You could have bromine, you could have iodine. Nobody uses fluorine. And your R group could be anything, okay? It could be any alkyl group, could be another aryl group, okay? So these acid halide, that's what they call generally. So depending on the type of R groups that you have, if it's from acetic acid, you get acetyl chloride, and X is chlorine. Okay, so in this case, your benzene is acting as your nucleophile, is a nucleophilic aromatic substitution reaction, right? So the first step is in the mechanism is when you, I hate drawing it this way. Let's get used to skeletal structure, please. That's much easier. Okay, so when you have these treated with your aluminum trichloride, it is going to generate your electrophile, okay, and this is resonance stabilized by the lone pair of electrons you have on the oxygen. One, two, three. Plus. Okay, I'm not showing the carbon in there, that's why I'm leaving a space here, okay? That's how to represent that. This is the same thing as CH3, C, triple bond, O plus. Okay, so that's the same thing as that. So this is your electrophile, and that electrophile is going to react with your benzene. So your benzene is your nucleophile with the lone pair of electrons you have in the ring. Sorry, I just want to draw two. Okay, so this is going to attack this carbon here. This will break. I'll use this to erase that electron there. Okay, that will come onto the oxygen. Just a reminder, you can review that. So now you have Okay. I'm going to show this hydrogen here. I'm going to put positive charge here. Actually, it's the other way, right? Sorry, it's the other way. Oh, boy. Can I erase this?
Yes.
I'm going to do this way. So hopefully you've not drawn the hydrogen. You can keep what you have. I don't want to draw the hydrogen. The hydrogen is drawn in the wrong way. Okay, so your acyl group is here. Your positive charge is here. And your hydrogen is here. Where should I put it? Let me draw it down here. Well, let me put it up here. Oh my goodness, it's going to be messy. Okay. Alright, so I'm showing that hydrogen. Because acyl nucleophilic substitution reaction on the aromatic ring is just substituting one of the hydrogens, okay, in the ring. So basically, you're substituting this hydrogen with the acyl group that is coming in, right? Okay, so at this point, this is going to act as your base, taking that proton, and you will re-aromatize the ring. So you have cross this out, okay? So you have your acyl group, plus of course your Cl and the catalyst that you started with. So that's how you get the acyl group on there. You can review this in chapter 16 to know more about it. Okay. So depending on the type of acyl group you're trying to introduce, you use the corresponding acid halide, right? So just now put this up there. Let's say you're asked to make this, right? Through Friedel-Crafts acylation reaction. This is what came onto the ring, right? So your starting substrate is going to be your benzene plus your, let me put X there. Your X could be chlorine, bromine, iodine. So you choose one of those. Don't just write X. You have to write the exact atom that you're putting in there. Okay? So, and when you combine those two together in the presence of aluminum trichloride, you get that acyl group on the benzene ring. Okay? Alright, reaction number 4. So, hydration of terminal alkynes. So this spans out any reaction now that we've covered in 251. Alkene, alcohol, well, alcohol was this semester. In the past, we used to teach it in the first semester. So alcohol, alkenes, benzene, and now alkyne, right? Okay. So hydration of alkyne, so that means addition of water. Hydration is addition of water, right? Addition of water. Okay. So in alkyne, it's catalyzed by mercury salt. Okay. And you generate ketone. These are referred to as methyl ketones. Okay, there are reactions that you're going to do to test those. Usually in the lab, you're going to do a test for the metyl ketones using iodoform test, right? But the mechanism will be taught to you later. So these are called metyl ketones. How do you get the metyl ketones? Well, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5. We have triple bond there, so we have to be careful of the angle. 1, 2, 3, 4, 5. That's 6. Okay. So the first step in the reaction is the triple bond picking up the proton. So your proton is added here, and your positive charge is going to be here by Markov-Dikov rule, correct? Mm-hmm. So the next step now is going to be addition of water to that electrophilic carbon. So I'm going to take this here and add it to that carbon. Let's draw the arrow down here. 2, 3, 4, 5. There we are. So the water comes here. Okay. Well, since we're showing magnesium, let's show everything. We don't want to skip it like magma-ready. Okay, so you have that, and another water molecule is going to act at this point as a base, picking up this proton, and you generate your 1, 2, 3, 4, 5, 6. This is your enol, alcohol, alkene. So alcohol and alkene, it's your enol. So that enol is going to tautomerize okay, to get 1, 2, 3, 4, 5, 6. Get your methyl ketone. That's the general name, but if you want to name this by IUPAC, it will be what? 1, 2, 3, 4, 5, 6. So it's 2 what?
2 hexanons.
That's correct. So 2 hexanon is an example of a methyl ketone. Okay? If you're wondering how the tautomerism occur, well, just push the electron around. I don't want to make this very messy. I could write it here, but it's going to be very messy. So let's put it over here. So how do you get the tautomerism? Well, so hydrogen bond. So these pi electrons can be used to pick up this proton in the polar covalent bond that you have between oxygen and hydrogen, and that bond will break actually. Okay, so now you have the hydrogen is there. Let me just draw it out to show where it went. This oxygen can be negatively charged, so that means this is positively charged because we've broken the bond. And it's to reform. Okay. So that's how you get that. But in a one-step mechanism, you can this way. Speak that. This comes here, and that completes the cycle. that's how the tautomerism works.
Question.
Yes.
So what did you say tautomerism happens by proton transfer?
Well, it's a form of proton transfer. Yeah, it's a rearrangement of bonds, right? But don't just call it proton transfer, because then proton transfer on what kind of alcohol, right? So this is actually not an alcohol, it's an enol, right? So if you have an enol, it's basically a rearrangement of the bonds in, the rearrangement of the bonds in the pi bonds, right? Okay, so you can call it proton transfer. It's fine.
Okay.
You're just moving one proton to the other.
Right.
It works. That's okay. Okay. So what page number was that? Page number 7. Okay, so let me go this page 7A, so that when I'm scanning it, or 7B actually. So when I'm scanning that, I know. All right. Another reaction for making a metal ketone is Gilman reaction. Gilman reaction, and we covered Gilman reaction under what chapter? Well, okay, you don't know the chapter. Under what under what functional group did we cover Gilman reaction? Which functional group were we talking about when we covered Gilman reaction? Gilman reagent. Where do you make them from? Alkyl halides. Okay, alkyl halides. So you have to review that. Okay. So now we've covered almost all the functional groups from 251, right? So you can't afford to forget anything. Sorry, you can. They are just connected, too connected. All right. So Gilman reagent is an alkylating reagent, just like your Grignard. So it adds alkyl group to an electrophilic center, just like your Grignard, but it's a mild alkylating reagent. It's weaker than Grignard reagents. Okay. So you can put a note that one of these alkyl group the carbonyl, just a note to yourself. Okay, so it's just one of those alkyl groups that will be added to the carbonyl, replacing your halogen. All right, replacing your halogen. So 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So when you have your copper, metal, stabilized by the lithium. Okay, so this is not acting as an alkyl group. It's going to attack that. 3, 4, 5, 6. So now you have metal group here that just came in. You have the chlorine. Okay. Of course, this will be stabilized by your lithium. And then you have copper, metal, copper. You have the methyl couplet coming off as neutral side product. So this will form the carbonyl. Halogens are a very good leaving group. Remember that. So this will leave. Now you have 2, 3, 4, 5, 6. With the methyl group that you just introduced, I'm just going to draw that out to show that it just came in. And to keep track of your, if you want to, okay, but nobody cares about this. We don't care about this. It's just to account for the atoms. Okay. So the question you should be asking yourself now, even though we're giving you the Gilman reagent, is how do you form the Gilman reagent, right? So you have to revisit that. How do you form the Gilman reagent? Okay. You know that the Gilman reagent will perform these transformations, but you may be given the question in a different form, where you're asked to make this using Gilman reaction. So that means you have to think about the alkyl halide you make that you're going to use. What base are you going to treat it with to get your Gilman reagent? So you need to revisit that. Okay? Make sense? Okay, so those are the few ways to make aldehydes and ketones. There are other ways to make them that's beyond the scope of this, like Wittig reaction, for example. Wittig reaction is another way to make a ketone from an alkene. I'm sorry. Wittig reaction. Oh, okay, that's under reaction of carbonyl. Okay, that's all right. Let's go there. It's beyond the scope of this. In the Wittig reaction, you convert a ketone to an alkene. So, talking about the reaction now. That's where we're going right now. I don't think we have Wittig here anywhere, but we'll see. Okay, so that's how to make. Let's quickly review that. How do you make aldehydes and ketones? The first reaction, in any order. Any other. Let's do that quickly. The first reaction, of course, Gilman is the last one, so that's easy to remember, right? What other reaction?
Oxidation.
Huh?
No. Oxidation.
PCC of what?
Primary alcohol.
What are you converting to what?
Primary alcohol to aldehyde.
Using PCC, right? All right, if you want to make ketone, you second, right?
Or
Okay.
DMP.
Or DMP, yeah.
You can only
Desmartin
use
periodinane. Yeah. Okay.
or chromium.
So if I were you, here's what I'll do. I'll list all the functional group that you can convert to aldehyde and ketone. So I'll say alcohol, alkene, alkyne, alkyl halide, and which other one? That's about it, right? So alcohol, that's group number one, alcohol, alkene, alkyne, alkyl halide, and esters.
Ester.
Okay? And then you draw an arrow with the reagents that you will use to get you the type of aldehydes or ketones, right? That makes it easy. Okay? All right, now let's do the reactions. I forgot my phone, so yeah. All right. So the reaction. Again, these are things that we've talked about, so we're just gonna breeze through it. Now, aldehyde can further be oxidized to carboxylic acid because they have this hydrogen that is oxidizable in them, but ketones do not. Okay? So that means you can oxidize aldehyde to carboxylic acid. Okay? So you can oxidize aldehyde to carboxylic acid. And any chromium-based reagent will do that. Okay, so like a revision of what we talked about. So any chromium-based reagent will do that. If you have a very sensitive functional group that can further be oxidized, you can use a mild oxidizing agent instead of a chromium-based, like silver oxide is another oxidizing agent, right? So aside from PCC, you can use silver oxide, okay? So silver oxide will oxidize your aldehyde functional group to carboxylic acid. functional group. Okay? And that's an aldehyde functional group. Okay, so here's the reaction I was talking to you about, that even though we know or we say that ketone cannot further be oxidized, in some cases you can, okay? And here's the reason why. Because to every ketone, you have a very tiny amount of its tautomer that can be oxidatively cleaved, okay? And so that can be oxidized because it's a vinylic hair, can be oxidized to this guy, to dicarboxylic acid. And that can only be done in a hot alkaline potassium permanganate. Okay? And remember, in the synthesis of your alkene, you use that as one of the tests. Even though we didn't use the hot alkaline one, we use potassium permanganate to oxidize our, to oxidatively cleave our double bond. You guys remember that? It's been a while, right? Okay. So this is also possible. All right. Just remember the reagent you can use for that. Okay. So that will cleave either this bond or that bond, as long as it has hydrogen on it. Okay. So that's oxidation. Now, the next set of reaction that we're going to consider is nucleophilic addition reaction. Let me just give the. So, we talked about aldehyde and ketone, and we're focusing on the electrophilic carbon and the nucleophilic oxygen as the reaction site. Okay, so generally, because this carbon and that carbon is electrophilic, if you treat either of them, so this is the general form that this reaction is going to take. If you treat it with a nucleophile, that nucleophile is going to add onto the electrophilic carbon center, breaking the carbonyl oxygen double bond. So you're going from sp2 to sp3 hybridized carbon. Now, because the hydrogen or the alkyl group that you have there is a poor leaving group, nothing is going to happen further. This will just pick up a proton and become an alcohol with the addition of your nucleophile. So that's why all the reactions that you're going to see in this case are referred to as nucleophilic addition reaction. That is basically their general mechanism. Okay. Now, what you have to identify are the different types of nucleophile. So you could have charged nucleophile, for example, base, your halogens. What else? If you have charged sulfur, if you have a nucleophilic carbon, as in the Grignard, right? Okay, so those are charged. Well, there could be more of them, but charged nucleophile. Okay, and then you can also have neutral nucleophile. Okay, so oxygen could be part of it, right? Nitrogen with the low pair of electron, sulfur. What else can we think of? Your double bond, your triple bond, right? So those could be your neutral nucleophile. So that's what we're going to learn going forward. How do these nucleophiles add onto the aldehyde functional group or the ketone functional group, okay? All right, we're going to stop there. So I'll see you guys on Wednesday. Remember the quiz on Wednesday, chapter 18, 30 minutes. All right.